All right, very well. Well, everybody, thank you for coming. Dear Minister Egelund, dear Excellencies and esteemed international guests, dear colleagues and friends. It is truly an honor to welcome you to the University of Copenhagen and this ERC event on competitiveness through frontier research. This meeting has been long in the making, and the world has changed dramatically since its inception, making it more relevant than ever. How do we even start to describe the turmoil that surrounds us? Actually, Charles Dickens did it well. In the famous opening lines from his novel A Tale of Two Cities, set in London and Paris before and during the French Revolution, Dickens thus wrote, "It was the best of times, it was the worst of times. It was the age of wisdom, it was the age of foolishness. It was the epoch of belief, it was the epoch of incredulity. It was the season of light, it was the season of darkness. It was the spring of hope, it was the winter of despair." It is arguably harder to find hope than despair these days, but the hope that we do have most definitely arises from science. Indeed, with the recent developments across the ocean, and with everything that is happening right now around us, we need to trust in science to literally save the world. This is true on so many levels, but not least at the fundamental level of furthering human knowledge for the sake of human knowledge. I remind you that it seems to be a historical prerogative of any despotic or fascist regime to decide for its people what knowledge is important and what human endeavors are unnecessary or even out of bounds. So in the current political climate, we not only need science to save the world, but we also need Europe to save, foster, and safeguard science for the sake of the world. And at the ERC, we are tasked with funding the very best science across Europe. And we do not tell the researchers what is important or what areas are worth investing in. The applicants and the experts that sit in judgment tell us that. So an ERC grant is a rather unique science funding instrument, not only in Europe, but in the world, across all science disciplines. We as Europeans can be truly proud of it. And importantly, the knowledge that is gathered this way is not dusty ivory tower stuff that no one can use. Indeed, by far the biggest group of successful applications at the European Innovation Council comprises present or former ERC grant holders, and 44% of all ERC grants are later cited in patents. In the case of life sciences, my domain, the number is even 66%. So beside ERC truly shining brightly as a lighthouse of science excellence and knowledge gathering, much of the bottom-up science funded by us is actually already translated into real-life problem solving. So with all this in mind, Europe needs to strive to enhance its position as a shining light of science and innovation. Briefly put, we Europeans must be brave and insist on it. So to put in the effort and fund science and innovation to help save human civilization. Thank you for helping to make this happen. Thanks. All right, but as the first speaker today, it is my great pleasure to introduce Christina Egelund, Danish Minister of Higher Education and Science. Minister Egelund is actually the 11th Minister of Science and Education in Denmark since 2010. Fortunately for us, Christina is breaking all recent records for staying power and has now been in post for almost 3 years. And wow, are we lucky to have her. The minister is really going out of her way to be here, but that also means that she has to rush off to another meeting right after her talks, so now you're warned. She has, however, kindly promised to return for our dinner later tonight. Christina, we are very grateful. The floor is yours.
Thank you so much, Jesper, for that introduction. Dear Maria, dear guests, thank you for inviting me today here where we mark the beginning of the ERC week here in Copenhagen, a whole week dedicated to excellent European research and innovation. And as Jesper mentioned, it is quite a busy day because today is also the official opening of our national parliaments. So today is also formative where we start important work to tackle difficult societal problems. I couldn't think of any place more meaningful to be on that specific day than here at the University of Copenhagen attending a ERC conference. So thank you so much for that. I have said this before, but I think it's worth repeating. For Europe to compete globally, we need world-class research, and the ERC is essential in making that possible. For nearly 2 decades, the ERC has produced remarkable results and opened extraordinary opportunities for some of Europe's brightest minds. It has grown into a symbol of excellence that we can all take pride in. Here in Denmark, we feel an extra connection as the idea for the ERC first took shape during the Danish presidency back in 2002. We like to think of ourselves as its unofficial founders. True or not, I think it is true. It is a great pleasure for me to welcome you all to Copenhagen for the ERC week. We are in a new world order where research and innovation are playing an increasingly important role in the future of our continent. Europe can no longer rely on others to come to our rescue when things get difficult. And that is whether it concerns energy, technology, or security. Our strategic autonomy has become an important factor, not because we want to turn our back to the world, but because we want to stand much stronger in it. Because we want to protect everything we believe in and have built together now when we see that values are shifting and alliances are changing. One of the founding fathers of the European Union, Jean Monnet, wrote in his memoir, "Tout est possible dans les moments exceptionnels à condition que l'on soit prêt, que l'on ait un projet clair à l'instant où tout est confus." Or in English, anything is possible in exceptional moments as long as you're ready, as long as you have a clear project at the moment when everything is confused. This is the exceptional moment where everything is a little bit confused. The world order, as we know, has known it since World War II, has changed. More than anything, we need a clear project and direction, and science and innovation are at the heart of that ambition. Europe is privileged by having some of the world's most talented researchers and innovators. There is an abundance of ideas across our continent. It is not talent we lack. But we need to get better at setting a direction. More of our ideas and research results can and should be transformed into businesses and products that can compete on the market and make a difference, so that Europe has the strength and innovation power to stand strong in a world that is changing. The global technology race is an important factor here. We need to invest strategically in the technologies of the future, quantum technology, artificial intelligence, biotech, and of course, space. Space is a good example of a critical technology of great importance for Europe. I see one clear goal: an innovative, diversified, and competitive European space sector. Space is not just about exploration. It is a critical technology that underpins our communication, our security, and our environmental monitoring. Our ability to compete globally depends fully on bold investments in innovation, and that starts with fundamental research. Excellent fundamental research is the seed from which tomorrow's breakthroughs grow. We should improve existing technologies and industries. but not neglect disruptive innovation which stems from investigator-driven frontier research. For too long, we have settled for solutions from the other side of the Atlantic when it comes to our critical technologies. This is no longer an option. We have to take responsibility and claim our space in the technological race. Universities play a crucial role in this, of course, both as research institutions and in the value chain from research to business. It is on university campuses that groundbreaking ideas are born. It is where talents are shaped. It is often where the foundation is laid for the entrepreneurs of the future. But if we are to turn more promising research into real commercial value, we also need to change the framework within the European Union. We can make it more attractive to be a business in Europe. The stakes in research and innovation have never been higher. It concerns the very future of our continent. It is about everything that we have built together. It is about who we are and also who we want to be. And because of this, we also need to safeguard the ideals of research and to work to strengthen European competitiveness and security. Academic freedom and international research collaboration are increasingly affected by great power interests and political control. We see this in China, where academic freedom often gives way to ideological conformity. Unfortunately, we also see it in the United States, where political tensions and culture wars interfere with universities' freedom to research and teach. This is why it is so important that we do not take academic freedom for granted. We must always protect the values that form the basis of free research and free education. It is what sustains scientific integrity and earns the public trust. And I am convinced that it is also our competitive strength that will help us attract and keep talent in Europe. So when we invest in European research, we must always do so with a commitment to academic freedom and democratic principles. In this ever-changing world, our values set us apart. As we begin the ERC week in Copenhagen, let us remember that research is not only about knowledge. It's also about direction, resilience, and ultimately about freedom. If we set a clear course, invest boldly, and protect the principles that make European science unique, then Europe will not only keep pace with the world, then we will help shape it. Together, we can ensure that the ERC remains a beacon of excellence, that our universities continue to be engines of innovation, and that European research strengthens both our competitiveness and our democracies. With the proposal from the European Commission on the Next Horizon Europe, there is a strong underlining of the importance of frontier research. As presidency, we will make sure to bring negotiations forward and not to lose sight of frontier research. That is how we stand stronger. That is how we can wisely use the exceptional moment in time to secure the future that we commonly want for Europe. Thank you.
All right. To introduce the next speaker, Rector of Copenhagen University, David Dreyer Lassen, is a professor of economics. He previously served as a pro-rector for research and innovation from 2021 to 2025. He has held several leadership roles, including chairman of Independent Research Fund Denmark and founding director of the Copenhagen Center for Social Data Science. He holds a PhD and a master's in economics from the University of Copenhagen, and his research focuses on political economy and the use of digital data in social science. As rector, David emphasizes the university's role in advancing world-class research, education, and societal impact. David is one of the very few, if not the only, serving leader of a major European university who's also been an ERC grant holder, which we are very proud of course, without saying. David.
Thank you very much, Jesper. So dear fellow researchers, former ministers, ambassadors, ladies and gentlemen, it is a real honor and privilege for me to welcome you all to the University of Copenhagen. And I would like to give a special thanks to Jesper and the entire team in organizing this. It's not easy organizing grand scale conferences, so thank you very much for providing this platform for us to discuss. This event is a celebration of two things: European collaboration and basic research, and they're both close to the mission of the University of Copenhagen. And fortunately, they're also close to each other. In fact, I would go so far as to say that the history of Europe and of basic research are deeply intertwined. If you go back 100 years, almost, to September 27, 1927, when Heisenberg, Curie, Einstein, and Bohr, among many of Europe's leading scientists of the time, they gathered in Brussels for the 5th Solvay Conference, the first post-World War I conference that again included German scientists. They were photographed in what has since been called the most intelligent picture ever taken. Not to put any pressure on present company, of course. The meetings and exchanges that took place back then were decisive, not only for the advancement of science in Europe, but also for shaping a European identity in science rooted in knowledge, curiosity, and the pursuit of understanding. And this brings me to the first, maybe obvious point, also made by the minister. Our status and self-perception as a global leader in knowledge is certainly not a given. It is a result of a sustained investment in the scientific talent, and it can shift, and it may sometimes be already shifting elsewhere if we lose focus. Many of you have read, or at least heard about, the reports on European competitiveness by Draghi, Letta, Heiter, who's here and will speak later. They all recognize essentially the same reality. European competitiveness is under pressure, and further investment in research and innovation is essential to maintaining Europe's resilience, relevance, and leadership. I know I am preaching to the choir here, but it is a message that must be repeated also with active politicians, such as our minister, in the rooms. You'll hear it again tonight. And Mr. Draghi's reflections on the occasion of the one-year anniversary of his report, which he gave just a few weeks ago in the European Commission, suggest, unfortunately, that not much has happened within the last year. But we're not here to compare ourselves to giants of the past, but I do feel hopeful looking around at the present company. So many brilliant minds gathered to exchange ideas and support basic research in Europe. And this is, of course, what the ERC Week is about, to share perspectives on how we best support and develop basic research at the European level. But before we go any further, you might ask, what is basic research really? There is, of course, a literature on that, a very interesting one at that, and I will here draw a little bit on the work of a science historian, Desiree Schouts. The first recorded use of the term basic research was in the United States in 1906 in the 19th annual report of the Agricultural Experiment Station in Lafayette, Indiana. The term basic research did not, and this was a surprise to me, arise out of the tradition of pure science, which had idealized research as an intrinsically philosophical search for eternal truth. Indeed, the description above the entrance to this university, where you will dine tonight, translates from Latin to seeing the heavenly light. No, on the contrary, and here I'm citing Schouts, these new concepts emerged in the late 19th, the early 20th century, at a time when society's expectations regarding the utility of science was in fact increasing sharply. So in order to manage expectations, funders like the US Department of Agriculture use the concept of basic research to bridge the gap between the promise of utility on the one hand and the uncertainty of the scientific endeavor, to provide economic and political room for fundamental research for the long term. Only after 1945, when US policy strongly shaped the notion of what we now think of as basic research, Vannevar's Bush, science, the endless frontier, did these concepts actually return to the older ideals of pure science. Today in practice, the lines between basic research as just high-risk foundational research and the search for eternal truth, the lines are blurred. We are seeking eternal truths. We are taking on massive risk. That is what universities are here for. And the magic ingredient is curiosity. It all starts with a researcher somewhere asking questions. Why is this? How is that? What happens if I? And down the line, of course, some promising ideas never made it out of the starting blocks, while other insights shape society in profound ways. Take quantum mechanics. We're celebrating the 100th anniversary of quantum mechanics, and we also had a Nobel Prize in it today, I believe. So when scientists, many of whom were at the Solvay conference back in the day, explored the strange behavior of particles in the early 20th century, they were not trying to build smartphones or GPS systems. Yet today, those discoveries underpin the technologies that we rely on every day in this room and are forming the basis for the next quantum revolution. Of course, the discovery of DNA structure was, too, the result of curiosity-driven research. Today, it is the foundation of modern medicine, biotechnology, and much more. So these examples tell the same story. Fundamental research is, as the minister said, the seed from which innovation grows, as in the Agricultural Research Station in Lafayette, Indiana in 1906. And without it, applied research has no soil to root in. And that brings me to my second point. Basic research is not a luxury, it is a necessity. It's society's long-term investment in resilience, preparedness, and progress. And when we support basic research, funding curiosity, we build the foundation for future discoveries, innovations, and solutions that will keep Europe competitive and resilient in a changing world. To succeed, we need the help of everyone we can find, and central to this effort is, of course, the European Framework Programme and the European Research Council. And I do want to emphasize maybe a fundamental principle here, the interconnectivity of the programs and initiatives. The ERC, the EIC, Pillar 2 of Horizon Europe, and national initiatives, they're not isolated. They form a complex web of interdependent strands, each essential and each influencing the others. And it works a little bit like a spider web. If you pull at one thread, the entire web shifts, sometimes in unpredictable ways. And as we consider reforms, whether reallocating funds, adjusting priorities, redefining frameworks, we must proceed with care and foresight. A change in one area can ripple across the entire ecosystem, affecting programs, researchers, institutions. And the strength of our research and innovation landscape depends on maintaining this delicate balance. If we pull too hard, too fast, if we cut strands in order to direct attention only to certain areas, we risk destabilizing that web, undermining both past progress and future potential. And as we've already heard, the core of our ecosystem must always be excellence. It is excellence that drives breakthroughs, fosters impactful discoveries, and elevates Europe's global scientific standing. It must remain our guiding light, ensuring that the investment will yield the highest quality research and solutions thereby to the grand challenges we face. So, all of you, all of us, remember to adopt a holistic perspective when designing and implementing reforms. The ultimate measure of our efforts here must be the excellence of the research we support, based on the researchers, the selection panels, and that excellence is the foundation upon which the innovation and societal progress is built. And the European Research Council, of course, has been transformative in supporting excellence without compromise. It attracts the brightest minds, fosters interdisciplinary knowledge, and it amplifies Europe's scientific voice on the global stage. So we do not only in this room, again, preaching to the choir only brings you so far. We also try to take it outside of this room to encourage the EU to provide the ERC with the resources and governance needed to safeguard its independence. A strong ERC will continue to deliver excellence for researchers, for universities, and for Europe. And with these words, I wish all of us a great conference. Thank you.
Thank you very much, David. I'll now introduce the first of our two keynote speakers on science matters. Anne Lullier is a professor of physics just across the Sound at Lund University in Sweden. She was awarded the 2023 Nobel Prize with Pierre Agostini and Ferenc Krauss for pioneering work on attosecond pulses of light. Joining Marie Curie as just one of just 5 women to ever receive the Nobel Prize in Physics. Anne is French by birth and studied mathematics and physics in Paris, earning her PhD there in 1986. She later worked in Sweden and then in the US at the Lawrence Livermore National Laboratory before joining Lund University in 1995, where she became professor of physics in 1997. In the 90s, she and collaborators explained so-called high harmonic generation in ionized noble gases using quantum mechanics, paving the way for the creation of attosecond light pulses in the early 2000s. Besides the Nobel Prize that marked those discoveries, her other honors include the L'Oréal UNESCO Award for Women in Science in 2011, and the Carl Zeiss Research Award, and the Blaise Pascal Medal, both in 2013. In the ERC sphere, Anne is highly unusual in not only being a triple ERC advanced grant holder, but also having had 2 proof of concept grants. Indeed, she has also been involved in the creation of a spin-off company, Sphere Ultrafast Photonics, where she's a co-founder, scientific partner, and advisor. Professor Lullier has kindly agreed to tell us about her scientific journey, and we look very much forward to it. Anne.
Thank you very much. So I'm going to tell you about my scientific journey and how it was influenced by European research programs. And I'm going to be a little bit broader than the ERC. I'm going to talk about other programs as well, which have been, as you will see, very important for my career. So beginning in France, and I did my PhD at the Commissariat à l'énergie atomique in Saclay, close to Paris, and defended in '86. I did a very small postdoc stay in Gothenburg, Chalmers University, and then I was recruited as a permanent researcher in Saclay. This was easier time, say, to get a permanent position at that time. July 1987, I had the chance to be part of an experiment that really was very important for my career. We focused an intense laser pulse into a jet of gas, rare gases, and we look at the light that is emitted from these atoms using a grating to analyze the radiation, and then we have a detector. And we were looking after fluorescence radiation from this jet of atoms, but what we saw instead was a generation of high-order harmonics of the laser field. So this was, we have talked about curiosity-driven research, was definitely the case. And in addition, you have this additional interest when you do experimental research. sometimes you see something which you did not expect. And it's really fascinating. And this was really the case in this case. So the numbers that you see here indicate the number of the harmonics. We only see odd order harmonics. And if you see 31, that means that the frequency of the light is equal to 31 times the laser frequency. What was very interesting, and this is an idea that came up a few years after this discovery, 1987, was the idea that possibly, so here I'm showing you these harmonics. These are waves with different frequency. If these harmonics happen to be phase-locked, which means in phase at a certain time, all the maxima happen to be at the same time, then if you add all of these waves, you get interferences, and in the middle, all the waves add together to make a very short light pulse. When they are not in phase, you have destructive interference, so that by these interferences, you can concentrate light into a very short light pulse in the range of attosecond. Attosecond is 10 to minus 18 seconds. So typically we talk about 100 attosecond. This was the first time we were even mentioning this time scale. So very exciting. But the question was, does this happen? Actually, it's going to take us 14 years to really could be able to measure the duration of attosecond pulse and answer yes. It's reasonably synchronized, reasonably phase-locked, enough to get these very short light pulses. Now we are at the beginning of the 90s. We built instrumentation dedicated to study these high-order harmonics. You have here a photograph of myself many years ago with my first student in France. His name is Philippe Balcou. And we built the instrument that you see, contains vacuum chamber. This instrument contains what we need, gas jet, optics to analyze the radiation, and then a photon detector. At the same time, in Sweden, they are making use of new laser technology that happened during this time, in particular the discovery of the chirp pulse amplification technique that led to Nobel Prize to Donna Strickland and Gérard Mourou in 2018. So they put together these new discoveries to build a laser laboratory in Lund, which at the time was really unique in Europe. So of course, and this laser was perfect to study high-order harmonic generation. So then came the idea, why don't we work together? So we were invited by Swedish scientists to come with the instrument that you see here to perform an experiment in their laboratory. Was it in the framework of a European program? Not yet. So we came in '92 to do these experiments, and actually we started discussing, why don't we make a research network? Lund, Saclay, London, Garching. There is a fifth that I don't remember at the moment. So we prepared this research network that actually was accepted 1 year later. At the same time, I went to United States, again in looking for the good lasers to do my research using this instrument that you have seen before. 1994, I decided to move to Lund. This was really private reason. I simply met 2 years before my future husband. So I start again my career, look for a position. I got an assistant professor position at Lund University in 1995 and professor position in 1997. I want to mention one experiment that we performed during this time. This was in 1997. we wanted to see whether this harmonic radiation is coherent. So in order to see that, what you do is you split the light into two, and you let the radiation diverge, and you look whether there is interferences or not. If light is coherent, you get interferences. If not, you don't. So we did this experiment together with my first PhD student in Sweden, who was Danish. So here I want to acknowledge she was coming from the University of Copenhagen, actually financed by the Niels Bohr Institute. And it was really great to have her working with me in Sweden. Mette Gårde, together with Theodor Hensch, that would get the Nobel Prize in 2005, and Marco Bellini from the Lens Institute in Florence, and this photo of myself again. How did we do that experiment? This is really European. You have 4 nationalities in this group here. We did that thanks to transnational access to laser infrastructure. This has been the case. All my career, I've benefited from the possibility thanks to this program. And this is laser infrastructures. Now it's called the Laser Lab Europe. Very important for my whole career to have this possibility to have researchers coming from other places in Europe to do experiment, and vice versa, we can send researchers, students to other places. 1999, I coordinated a network called ATO, Marie Curie Network, and the goal of this network was to really demonstrate the existence of this attosecond pulse. During all of these years, we had studied the high-order harmonics. We were convinced that, at least in some cases, yes, there could be attosecond pulse, but how can we measure them? This was really a big question at the time. And so we proposed this network. We didn't have a good idea how to measure attosecond pulse, but nevertheless, it was accepted by the European Union, and they were very, I think, clever to accept this network, because just after the following year, after we started, 2001, Pierre Agostini and his group demonstrated that we had 250 attosecond pulses in a train of pulses. And almost at the same time, Ferencváros and his group, then he was in Vienna, could generate single attosecond pulses and measure the duration of this attosecond pulse. You can see it's 530 attosecond. And if you look at the first results after this discovery, and this is really why they got the Nobel Prize together with me for this measurement. But if you look at the major results obtained in this field and kind of how could we get to shorter and shorter pulse, you have Garching, Lund, Milan, and the present record is in Zurich, 43 attosecond. European laboratories. And you can ask me, why is it only Europe? My own interpretation here is that because from the beginning of this field, we have worked together. We have worked together in networks, in this transnational access, and we have exchanged ideas, exchanged students. So very strong European community around this subject. I want to say a little more about Marie Curie actions that have been important during my whole career. So this is all the action I have myself or my group have been participating to. Starting in '93, you have almost all the different framework programs. The one with a frame, that's the networks I have coordinated myself. Again, very important, and it's really making people move across boundaries. Creating PhD position, for me, especially at the beginning when funding was not very important, was great to have this PhD student thanks to these actions. Plus possibility to have individual postdoctoral fellowships. ERC. ERC started in 2008, at least for me, I don't know. And so this was the first call. And at that time it was, the reputation in the research, for the researcher, that is going to be really tough. You need to be old, you need to have many Nature Science articles. The rumor was it's going to be extremely, extremely competitive. And I thought, well, I don't have many Nature Science, but maybe I'm a little bit competitive, I don't know. I say, I'll try anyway. It will don't work, but I will try. And it worked. So this is my first ERC grant, ALMA school. 5 years afterwards, I thought, this is, what I want to say is that this was really important for my career. This is really the time where the research group started to grow. And the reason is that it's not only got good funding, it really has a prestige, so that I think it's easier to get additional funding. And I think, I don't know it, because you never know it, but I'm convinced it has helped me to get funding from Sweden and from foundations, these kind of things. So after 5 years, this was finished. I thought, this is really too good funding. Maybe I should try again. And again, the rumor was that they are going to finance only only the people that have that apply for the first time. They don't want to finance another person another time. I said, okay, I'll try again. And yes, I got it. And this was a program PULP. And after 5 years, I decided, no, I'm not going to try a third time. But then I waited 1 more year and said, let's try one more time. And yes. And actually, I'm finishing this grant at the moment. It's finishing at the end of the year. Will I try a fourth time? Yes. I don't think so, actually. No. Anyway, if you wonder what this is about, the first was about light. It was about these attosecond pulses. The second was doing atomic physics in a different way using this attosecond pulse, measuring the time it takes for electron to be emitted for photoionization process. And then the third, which is ongoing, is really at the contact between our field, ultrafast physics, and quantum physics. Can we measure quantum state of electrons using our attosecond pulses? And this is what we are doing now. It's very, very fascinating. Okay, I think it was mentioned that also we used ERC for innovation. When you do experimental research, even though this research is very, very basic, it's also very technical. We work with advanced laser systems. And sometimes you have clever students that have ideas and come up with ways to characterize these laser pulses. And we have, actually, this happened 3 times. So we have 3 patents. We wrote 3 proof of concept applications that were accepted, maybe not directly, but after a couple of times. So corresponding to 3 different inventions. To get the first one, we thought, we need to create a spin-off company, which is called Sphere Ultrafast Photonics, and which is actually in Porto. You wonder why Porto? We are in Sweden. Why Porto? It's really almost the furthest you can go to in Europe. The reason is that the student that came up the idea of this technique called D-scan was a Portuguese student, and actually he did a double degree, both at Lund University and Porto University. And Porto University was simply much more eager to to create company and to develop this. So we're still working with them. They are still. It's a bit tough, the life of a spin-off company in this field, but after more than 10 years, 12 years, they are like 15 people working in the company, so I think it's going very well. And we made this device that you see here that are used to characterize laser pulses. When you work with very short pulses, it's important to know about the phase of the electric field, as well as here what is called the carrier envelope phase. This is the difference between the maximum of the envelope and the maximum of the electric field. So all of these things are devices to characterize the laser pulse. We even pushed the second device here with an EIC transition program, which is just finished. And we have submitted an EIC transition application for the last device here. We will see what happens. So I'm now coming to the end of this talk. Yeah, I just want to mention that I benefited so much from the ERC that at some point I got many, many letters from Jean-Pierre Bourguignon here somewhere asking me to be panel member, and I resisted a couple of years, but then at some point I said, yes, I am happy to be panel member, and I was during twice for Consolidator grant and twice for Synergy grant. This was a very good experience for me. My scientific journey has been supported by European programs, but of course not only, also by the Swedish Science Council. And in Sweden you have the Wallenberg Foundation, which is really financing basic research a lot. So I would say equivalently by Europe, if I count roughly the funding, I can find Europe 1/3, Swedish Council 1/3, and this Wallenberg Foundation 1/3. A scientific journey supported and recognized, as was mentioned. Maybe an important step in my career was my election to the Royal Swedish Academy of Sciences in 2004. For me, I had just been in Sweden less than 10 years. It was really a welcome from the Swedish scientific community. So it was a very important step. The UNESCO Laurel Award for Women in Sciences, and then recently the Wolf Prize and the Nobel Prize. With that, I would like to say that research, especially experimental research, is really a team work, and it's important to have certain critical mass to do good research. This critical mass is, of course, very different depending on what you are doing. In our field, it's good to be 10, 20, now we are almost 30 person. I'm happy to list here the nationalities of the people in my group. It's very European. I don't really know why, but we attract people from all over Europe. And finally, I would like to thank the European Union for helping me in this journey and for building bridges between countries in Europe. This is a photograph of the bridge between Sweden and Denmark, which I took the train this morning across this bridge. So thank you very much.
Thank you so much, Anne. It's now time for some questions. Please, when you ask a question, introduce yourself very briefly. Perhaps I can ask the first question, Anne. So I'm fascinated by the differences between different fields and how different fields balance the need for collaboration and, of course, the fierce competitiveness that is inherent in most great science. I mean, how did that work? And it worked for your field, but could you see this happening again, or has the world just become a tougher place in terms of competitiveness?
To me, collaboration is more important than competitiveness. I wish there was a little less competitiveness in some part of the science that we are doing. And you see that we are working with very short pulse lasers, and actually this community, it's called ultrafast, came into our field in the end of the 90s, and for some reason they are much more competitive than we are doing basic research about atoms exposed to strong laser fields. But I think it was good and bad. It was good because maybe they pushed us, but I think there is a little, again, I think there is a little too much competition sometimes. So to me, collaboration is really important, and I really think that European Union, with these different programs that I have named, has helped in this collaboration. And I'm thinking actually maybe not so much about ERC, but the Marie Curie actions and this transnational access to the infrastructures.
Right. And did you feel a big difference when you were then in the US, that the US was different? Because what we always hear is that certainly when I was there, it was different attitude. It was you were in it for yourself,
Exactly.
much more than collaboration. Was that the same then in your field?
Yes, it was. I can say that in maybe not now, but at the beginning, with a little funding, you have actually no choice. You have to collaborate, because otherwise you don't have the critical mass. And then we were in the US, they have more funding for research in general, and they had these bigger research teams. I think recently they have, I'm talking about before what is happening now, but recently they are copying us a little bit, trying to have these network programs and these excellence programs. So they have seen that what we are doing, and also making these infrastructures financed by the European Union. So they are a little bit copying us. Now, at what is happening now, I don't have a good idea. It seems very chaotic.
Yeah, right.
Yeah.
Manuel.
Thank you so much for this excellent presentation. Where would you like to be in 10 years' time? And how do you see cooperation with outside Europe, particularly with China or the United States? You mentioned China in one of your slides, but where would you like to be in 10 years' time, and how do we need to collaborate with others?
So I can first give you an answer, which is I'm going to be retired in and enjoy some more relaxed way of life. This was more a joke, but this is. So if I talk about like myself, but a bit younger, well, I think what I see in our research field is that China is making a progression which is enormous, and they are moving so fast, and they seem to have infinite funding. So they are building these attosecond facilities, for example. This is still an investment. It's not a big infrastructure, but still. And they are making not only one, but one in Shanghai, one in Beijing. It's very, very impressive. So I think in 10 years from now, we are going to be, science is going to be led by the Chinese scientists, and they will start getting the future Nobel Prize. Maybe there is some delay, but they will. I hope the US is recovering at some point. They are going to go down, but I hope they will go up again. And I hope Europe is still here. I mean, is still a major player in research. And there I would say the European Union has a huge role to play. It's going to depend whether Europe can stay together and whether these programs exist, and maybe even stronger. So this I'm completely convinced.
Other questions?
Ludovic Tilly, chair of the Coimbra Group of Universities. After your experience, what would be, in your views, the best instrument that we could either continue to develop or create to support a young PhD candidate currently working in a research lab in Europe to stay and to grow as you did?
It's a very difficult question. I think you can maybe answer more than I do. I mean, I like the European Research Council, and I see it's not only my own journey, I see what it does to other, and especially young researchers. So that's very important. But don't forget this collaboration issue. The ERC does not have that. Of course, you can include and collaborate, but it doesn't have this push to collaborate, which you have obviously in the Marie Curie actions, as well as in this access to infrastructure. So I think to push European people to collaborate with each other using these programs is important.
Thank you very much. Other questions? All right. Thank you very much, Anne.
Well, thank you.
All right. We continue our scientific journey with Sir David Klenerman. David is a professor of biophysical chemistry at the University of Cambridge. His innovative application of novel physical methods to biology and biomedicine has had a major impact on so many levels. Indeed, he co-invented next-generation DNA sequencing, which comprised some of the most important advances in biomedicine in the last decade or two. This invention was developed and commercialized by the spin-out company Solexa, which he co-founded. Solexa later became Illumina, the leader in the field of DNA sequencing. My lab uses Illumina sequencing practically every day, with their sequencing technology simply being the most widely adopted and used in most major sequencing centers around the world. This really has changed a lot. Sir David's recognitions include his knighthood in 2018 and the Royal Society's highly prestigious Royal Medal in 2018. He was awarded the 2020 Millennium Technology Prize jointly with Shankar Balasubramanian, and also the 2022 Breakthrough Prize for Life Sciences and the 2024 Gärtner Prize for Life Sciences, and also actually the Novo Nordisk Foundation Prize with Balasubramanian, and also for two of them with Pascal Meyer, all for next generation sequencing. So like Professor Lullier, Professor Klenerman has of course held prestigious ERC advance grants. Sir David, we look very much forward to hearing your story.
Thank you very much. So I was going to tell you sort of the backstory of how we came up with the idea for next generation DNA sequencing. So I was going to tell you a little bit about my background. I'm a physical chemist, and you're going to see more lasers in the next few slides. I'll tell you a little bit about single molecule fluorescence, which was sort of the germ that led to the idea for next generation DNA sequencing, certainly from my side, and then how the sequencing works. And sort of, if you lose track, that the main idea of the talk is to show you how new physical methods enable new sciences. So this is a picture of a younger version of me when I just did my degree. I did my degree at Cambridge. I studied natural sciences, but specialized in chemistry. I chose chemistry because physics seemed too abstract and biology too complex, but chemistry seemed just in the sweet spot where you could actually quantify things that seemed important. So I did my PhD with Ian Smith, who you can see up in the top corner. And this is a home-built instrument that you can see. So you can see at the back all the gas handling that I did myself. There's a big chamber, there's a gas chamber, and we were studying reactions in the gas phase that produce infrared excited molecules. And then in the front, there's a home-built infrared spectrometer. So the idea of the experiment was to detect the infrared radiation generated by these chemical reactions. So after this, I decided to go to the States and worked at Stanford with Dick Zare for a couple of years, trying to use lasers to cut chemical bonds at specific positions. Rather unsuccessfully, we were very good at heating them up, but not very good at cleaving the molecule where we wanted. And then I returned and I got a job with British Petroleum just outside London near Heathrow Airport. So there's me with a less fancy than you've just heard of laser system, which only produces picoseconds. And we were using this to tackle oil industry problems. So just like you've heard a little bit about, here we were generating doubling light, second generation at surfaces. And this enabled us to watch corrosion inhibitors bind to corroding metal surfaces, or look at lubricants binding to metal surfaces, the types of problems that BP were very interested in. And what I learned, I think, being at BP, was I didn't have to understand corrosion inhibition. I just needed to be able to understand the laser spectroscopy and work with someone who understood corrosion inhibition. And together we could tackle much bigger and more complicated problems. And that's something that I took with me when I returned to Cambridge in 1994. So one of the big exciting things for a physical chemist in the mid-90s was the ability to detect single molecules. So chemists talk about molecules, but when we do experiments, we look at billions of molecules, not individual molecules. But the technique was developed to look at individual molecules, and it's based by having a dye molecule, and you excite it with a green laser like a laser pointer, and it will produce a yellow photon. But one molecule can go around this cycle 1 million or 10 million times before it blows up and undergoes a chemical reaction in its excited state. And 10 million photons is very easily detectable using modern technology. So this opened the door to watch biology in action. We could take our dye molecule, attach it to biological molecule of interest, and follow that biological molecule inside a cell. And as I'll show you later, it's also the ultimate in miniaturization, which is one of the ideas behind next generation DNA sequencing. So here's another picture of a laser lab. So the laser labs are typically in the basement where it's very stable in the dark. So you can see we've got a bank of lasers, deep blue, Cambridge blue, green and red, that are all relayed over to an inverted microscope, where here we've got, as it's shown in the bottom, a live T cell. And if you remember your basic physics, light at a critical angle will go a total internal reflection, but there's a small evanescent wave that propagates above the glass surface. So this is going to excite the basal surface of this T cell. And the T cell has a molecule called a T cell receptor, which is the basis of the adaptive immune response. And we're going to tag it with a dye molecule. And then we're going to watch the T cell receptor diffuse around on the cell surface. So the video is real time watching these single molecules move around on the surface of a T cell. So this was very exciting when we first saw this. And we're doing a lot of work trying to understand how the T cell receptor is organized in the resting cell and how it reorganized during the process of recognizing an infected cell and triggers, and how this process is so fast and so selective. So the first grant that I applied for when I got to Cambridge was in 1995, funded by the Biotechnology Research Council. And the experiment is shown in this schematic here. So you have this template primer of DNA attached to the surface. The oval is an enzyme called a DNA polymerase, which can copy DNA. And we have fluorophore labeled nucleotides. We wanted to watch this polymerase copying DNA in real time, a really fundamental process in biology. So I'm now just going to have a little bit of an interlude where I introduce you a little bit more to DNA. It's the deoxyribonucleic acid. It's almost in all our cells in the body, and it contains information stored as the 4 chemical bases: adenine, guanine, cytosine, and thymine. So A, G, C, and T. And the order of these bases tells you how to construct proteins and build and maintain an organism. And the DNA can be copied in new cells since it's a code. A always pairs with T and G always pairs with C. And decoding the DNA requires sequencing technology. So why would you want to sequence DNA? So you can understand life. DNA is fundamental to life. We can understand the difference between all of us in the room. We differ by one base in 1,000. We could find the causes of diseases. We could detect and diagnose diseases. We could hopefully prevent people getting diseases by intervening before they actually had the symptoms of the disease. We could find the most effective treatment, and we could monitor the treatment as the patient was given this treatment. But the human genome has 3 billion bases. So at the time, the technology that was used to sequence DNA, so this is back in the 1997, was also developed in Cambridge by Fred Sanger at the LMB. So I'll just briefly talk you through how this was done. So I explained to you DNA exists as 2 strands, and you can copy the DNA. So you have a polymerase, that's the enzyme that copies the DNA, the nucleotide triphosphates, and in the Sanger sequencing, you have nucleotide triphosphates that are terminated, so you can't add more bases onto these, and these are color-coded. So as it shows, what you do is start the DNA off with a primer. The polymerase then copies the DNA, and you're going to produce large numbers of copies, but occasionally it's going to be blocked by the terminator. So you're going to end up with, as it's shown in 3, a whole series of DNA of different lengths, one that got blocked early, one that got blocked later, and then you can run these down a gel and identify the fluorophore that codes for the terminal base, and from that you can reconstruct the sequence of the DNA. So the key thing to note, this is done in a tube, and typically you could do 500 bases per run. So to get the consensus human genome, this isn't the genome of an individual, this is the sort of average genome of all of us, cost $3 billion, so $1 per base. And at the time, back in 1997, the cost to resequence an individual to see all the differences cost $30 to $50 million. And the challenge was how you could sequence a human genome for $1,000 or less. So just to stress, we weren't thinking about DNA sequencing. We were just very excited about the ability to see single molecules, and we're trying to develop this method to copy, watch DNA being copied in real time using single molecule fluorescence with my 2 postdocs, Colin Barnes and Mark Osborne. So what we did after work, there's a pub very close to the chemistry department called the Panton Arms. We went and discussed the experiment. So this is a slightly misunderstood slide. It's not that the whole idea came in an alcohol-induced haze by drinking large amounts of beer. It was because we actually talked to each other. We learnt about DNA from Shankar. He learnt about single molecule fluorescence from us. And what we realized is we could repurpose the experiment we were trying to do and come up with a new way of sequencing DNA. So this is the idea that we came up with. We have our template prime of DNA attached to a surface. We've got our polymerase to copy the DNA. We've got our nucleotide triphosphates, which are color-coded, but this time they're very special nucleotide triphosphates that Shankar's designed. So what's going to happen is we've got a T. The polymerase is going to put the complementary base, which is an A, which is color-coded, next to the T. And then we're going to read that base, but this is a special base. We can remove the fluorophore, we can remove the termination, and then we can repeat this cycle again and again and again. So we can sequence the same strand of DNA again and again and again to work out the sequence of that strand. And the other key idea was we're going to take the DNA, fragment it, and attach it to the surface in a way that each molecule is roughly about a micron apart, so we can optically resolve it. And we're going to sequence millions of strands of DNA at the same time in this massively parallel fashion. And then we're going to take these short reads of maybe 25 bases of DNA and reassemble them back, since we have the consensus sequence, into the whole human genome. So if there was a eureka moment in the whole process, for me it was when I did this calculation in my head, back in 1997 on a plane flight out to a friend's wedding. So the calculation is as follows. The human genome has 3 times 10 to the 9 bases. I'm going to assume that we're going to have this array of 300 and 300 single strands of DNA, and I'm going to assume it takes 10 seconds to detect the fluorophores that have been incorporated. So that means I can sequence at about 10 to the 4 bases per second, so 10 kilobases per second. So one machine is going to take 3 times 10 to the 9 divided by 10 to the 4 seconds, so roughly 5 days to sequence a human genome. So we imagine this was a pathway to sequence billions of bases at low cost. So the next question was, what do we do? So we could write a grant to do this, but we had a conversation with, in Cambridge, the colleges, and the head of the college I'm at, Christ, was someone called Alan Munro. And Alan convinced me and Shankar that we were going to need exponential increasing amounts of money to develop this technology, and we should form a company. And this turned out to be very good advice. At the point that Solexa was taken over by Illumina, we've employed 150 people, all entirely focused on developing the technology, and we've spent about $170 million. So that wouldn't have been possible via research grants. So we formed a company. The company was called Solexa, and it doesn't mean anything. It's sort of a play on words, single mole. Shankar thought any good company like Xerox has an X in it, so it's called Solexa. And that's how we came up with the name. So these are the nucleotide triphosphates that Shankar designed. So we have a cleavable linker to cleave off the fluorophore and a reversible terminator so we can restart the sequencing again. Just to note, we don't end up with an entirely natural nucleotide when we do this cleavage, and we had to mutate the polymerase to be able to deal with that. So that's exactly what the company did, apart from one important difference. So instead of sequencing single molecules, it simplified the technology, and we could have a much more simple instrument. If we took a technology developed by Pascal Meyer that could take a single molecule on the surface and amplify it into a copy of the same molecule, but 100 copies in the same place. So we did this solid phase amplification. So this is what an early version looks like. You see all these spots. These are these individual colonies. So 100 microns is roughly a human hair, to give you some idea of how paralyzed it is. And we're going to watch each cycle the different colors and keep a note of that. And then we can reassemble the human genome. So in 2006, so just to keep a score of the time, in 1997 we came up with the idea. Less than 10 years later, we got a machine, which is shown with the Solexa logo, which could sequence 1 billion bases per run. And in 2021, after being taken over by Illumina, an awful lot more work done by all the people at Illumina, we could sequence 6 trillion bases per run. So in 1997, the number of bases per instrument was roughly about 10 to the 5. And then in 2021, it had gone up to 10 to the 13, an improvement of a factor of 10 to the 8. The number of sequencing lanes had gone from 100 to 10 to the 10, an improvement of a factor of 10 to the 8. And the cost, which is probably the most important thing, had gone down from about $1 billion to it's now at $200, a reduction of about a factor of 1 million. So in all honesty, this was well beyond our expectations in terms of what was possible. And it was only because there was a large number of talented people, firstly at Solexa, and then at Illumina, who really developed the technology to the point it is at today. But as a result of this, you've gone from this situation. So this is the front cover of Science in 2000. There's some sort of cocktail party, and there's this frog talking to this fly saying, well, have you had your genome sequenced? And in 2009, we published the first human genome. This is the human genome of an individual Afro-American. So again, just 12 years going from a concept literally written down on a piece of paper to sequencing a human genome. And that wouldn't have been possible if we hadn't formed the company. So I just... the number of genomes, the first human genome was sequenced in 2001. So just to note that the y-axis is logarithmic. So up to 2005, only about 100 genomes have been sequenced. Our instrument was on sale in around 2007. You can see this inflection point, and the number of genomes goes up rapidly. And the slide's out of date. I think there are about 50 million human genomes that have been sequenced. I think about 80–90% on the Alexa Illumina technology. In terms of the cost has gone down phenomenally. And so this is a plot of the cost against time. And the cost is now down at about $200 per genome. I mean, the other thing that strikes me looking back at this is that the Alexa Illumina technology is still the dominant technology 20 years on. We haven't really been replaced by something better or cheaper. So this has been widely used. So in the UK, there's the 100,000 genome, where 100,000 people were sequenced, and then we have their medical history, so we can see what genes predispose people to develop cancer or not develop cancer. And in Europe, you've just started the Genomes of Europe project, so you're going to sequence more than a million genomes to understand the ethnic diversity of all the Europeans. And so lastly, I just wanted to talk you through some medical applications. So when we came up with the idea, we thought it was initially going to be a discovery tool for scientists, but it's surprising that it's already translated into medicine. So in this example, we have someone who's got lung cancer. So what you're going to do is take a biopsy of the cancer and the normal lung, and then you're going to sequence them. And then what you're going to do is ask, what is the difference between the cancer and the normal tissue? You're going to use a triage, so you can ask, are the mutations in coding regions that will lead to cancer? And from that, you can work out potential treatment and then give the patient a treatment specifically for their cancer. The second example is, again, cancer. In cancers, a small amount of the DNA from the cancer leaks into the blood. It only lasts about 30 minutes, but if you sequence at a sufficient depth, you see a lot of normal DNA, and you can detect this tiny amount of cancerous DNA. And again, you can work out what the mutation is, and again, come up with a treatment for the patient. The next example, is closer to home. So this is a picture of two parents and a child at our local hospital, Addenbrooke's Hospital, which was on the local news. And what happened is a lot of babies are born with rare diseases, and there's often no treatment, and unfortunately the baby dies. But using next generation sequencing, you can sequence the mother, the father, and the baby. You can look for mutations in the baby's genome, which could explain their disease. In about half the cases, you can identify what's wrong, and there's straightforward treatments. And in this news article, they showed two very happy parents and a very healthy baby at home as a result of being sequenced using the Alexa Illumina technology. And it was widely used during the pandemic. So again, this is a logarithmic scale on the y-axis. Just a large number of COVID genomes were sequenced to survey how the virus was mutating and try and anticipate how it's mutating and control the spread of the disease. So I just wanted to finish with some reflections. The original idea came from basic multidisciplinary science. I think at Cambridge we had the right culture that facilitated talking across disciplines. And this was helped by a college system where we have people from all the different disciplines all attached to a college, organized in order to do the teaching. Another key point was we talked to Alan Munro. We had access in our university to people who had already founded spin-outs and could advise us. And most importantly, we tried to explore if our idea was going to work or not, and got the chance to try it out. You just wonder how many people have equally good ideas who never get the opportunity to try them. We got access to sufficient and quality risk capital. So the venture capitalists just didn't provide money, they provided a lot of expertise and experience that was very important in growing the company. And like I said, ultimately we had $170 million spent on us when we merged with Illumina, and 150 people working with us. The only sort of black spot with the whole experience is that we really failed to keep the company in the UK. And so if we're going to do this again, we need mechanisms to try and keep our successful companies in the UK, not ending up in San Diego in our case. So again, it's curiosity, multidisciplinary science that led to this idea. We're continuing to use the single molecule fluorescence to try and understand the molecular basis of neurodegenerative disease. And we've got very promising data using it for early diagnosis of these diseases using blood-based samples. So we're very excited about that. And I think that the Celexa story is really a great example of how physical sciences can solve major societal problems and improve people's lives. And I'll happily answer any questions that you have.
Other questions?
Wonderful. Lots of questions and lots of things to talk about. But I want to I'd like to return to that last point, because that is what many in Europe are obsessing about. Why we, manage to have the inventions and the insight and the fundamental science that leads to those, but then fail to scale up. So what are your thoughts on, or your insight on why it went to Illumina and didn't, you said didn't stay in the UK, could have stayed in Europe maybe. So why did that not happen?
It's complicated. I think that one fundamental answer is that the founders don't have control over the company. The VCs have a controlling stake and control the direction of travel. In our case, it was complicated because initially we did a reverse buyout of a company called Lynx Therapeutics that was founded by Sidney Brenner that was on the NASDAQ. And we did that because we thought they had a lot of good engineering experience that we would actually need. So that was a strategic decision to improve the company. But then it turned out we didn't need that technology, and then we merged with Illumina. But at the time, the merger with Illumina was a good option. They had all the sales force, but didn't have a sequencing company, sequencing technology. And, the combination, if you look at the share price, it went up phenomenally for a while. So I think we lost control. So I think the only way is like a golden share, some sort of system where the government or the EU invests in the company and prevents it going overseas. I think, in my view, that's the only way of stopping this happening. And I think we do want to stop it happening, because I think if we could have a virtuous cycle where the company success stayed locally, you have the people locally who then put their money back into the next startup. I think we just need one of these and the whole thing would grow. We just haven't managed to do that. So golden share, I think, would be, in my view, but I'm not an expert. I came to find out from you guys how you would stop this happening. But I would do something like that to try and keep it in the country. And I think it's easier now than it was back then. I think there's a much bigger network around Cambridge. People are more sensitive about this. But there is VC capital, but it tends to tail off when you need hundreds of millions. And I think the American VCs are less risk averse and prepared to take bigger bets than the UK VCs. I wouldn't comment on the European VCs.
Thanks very much, David. It's Harriet Bulkley here. I'm currently at Durham University and Utrecht University, but in 1997 I was living in a house on Panton Street, going to that pub. But I failed to discover such a brilliant technology as you did during my drinking days there. But I'm wondering whether you might tell us a little bit about how you think universities that don't have the same kind of density that you've talked about in terms of Cambridge, the college system, the density of connections between departments that fostered that multidisciplinary, interdisciplinary conversations that ultimately led to this kind of breakthrough. Where you don't have that kind of rich tapestry, what is it that both other universities and also research funders can do to try to support that kind of density of connections and collaboration that seems to have been so important here, apart from taking everyone to the Panton Arms, which obviously would be a good idea.
I mean, I think it's very difficult. I think it's a cultural thing and so you need people who've seen that culture work and buy into it. But I think you basically would have to organise events where you deliberately mix up different fields. You have well-chosen speakers, you maybe some outside speakers, and have these events to just try and mix up the type of science that people are exposed to, get them to meet each other. And you know, if you haven't got a local story, get someone in, you know, get someone like us to come in and tell our story, just to inspire people. And I think you just have to work at it more. I think it's not. I think that the Cambridge system facilitates this. It's not the golden ticket. It's just makes it easier. And I would say was one contributor to the success. But I think you can do it. You don't need to be in Cambridge, but you just need to work at it harder.
We do. Which are the main challenges to continue further improving your system and decreasing the costs for sequencing to really massify early detection and to effectively decrease the number of deaths in cancer?
I think the technology is reaching a sort of ceiling of cost. You know, you start to reach a point where just storing the data, it becomes a major cost. So I think in terms of medical application, it's more about working out how to interpret the data and what you need to do. But it's sort of reaching a tipping point where it would be more cost effective if you sequence all the newborn babies. So you have their sequence, you only have to do that once. And then you would, when you go to the doctor, you'd have someone's genome and you could work out what disease they're likely to have and try and take preventative measures before they developed type 2 diabetes, which is very expensive. So I don't think that the cost really needs to come down, and it's very hard to see how it will. I think smart application of the technology I think is what's needed now.
All right, thank you. Are there any other questions? I have one, but I don't want to ask it if somebody else has a question. Oh.
It's a great story, David, obviously, but there's obviously a lineage here from the double helix to Sanger to you, isn't there, in Cambridge? We're all very envious. But is the next frontier the epigenome? Are there any plans to get rapid analysis of the epigenetic changes? Because that probably will be the next step. But eventually all our genomes are sequenced, as you say. So,
I mean, I think that there's, a whole level of detail, this epigenome, but then you have to do that in every individual cell in your body. So it's vast amounts of data collection. So I think the epigenome would be a situation where you work out what the important aspects are and what important cells. So you would need to do this discovery and then focus in on what's needed, which is sort of originally how we thought about the sequencing. But since the cost has gone down so much, instead of just sequencing little bits, you just might as well sequence the whole thing. So I agree, the epigenome, but I think there's an awful lot one can do with straight DNA in terms of helping improving human health.
All right, I just have one final question. You're saying that nothing has really happened technology-wise in sequence over the last 20 years. Yeah. So is there a new frontier? Is there a new way of doing it that would make this much faster? Because it's not really the cost anymore, it's the time consumption in doing all this.
I mean, hopefully I didn't say nothing had happened. What I tried to say is despite things happening, it's still the dominant sequencing technology. Right. Yeah. So there are a whole bunch of other technologies. There's our rival Oxford nanopore technology, which has a pore and the DNA goes through the pore. And it's very fast, but for the last decade, it's been very inaccurate as well. So it's a bit like the tortoise and the hare story. But now the accuracy has improved. But it doesn't really compete on cost, which is really the key thing in terms of doing experiments at scale. I mean, they say you can do it in the jungle, but that I'm not sure that's a big advantage, given that you can ship the DNA within 24 hours to any sequencing lab. It's good at base modifications, so for the epigenome, it's good. And then this idea of doing it at point of care for diseases like sepsis. But those diseases, you typically only have 1 to 10 bacteria per ml of blood. So the challenge isn't the sequencing. The challenge is getting enough DNA to actually do the sequencing. So I think it's difficult to see if it's worth spending sufficient amount of money to improve the sequencing by any of the metrics like speed. What's that going to buy you in terms of why would you spend money developing that? I think it's sort of reached a plateau now.
Right. All right. Oh, there's one more.
Yeah, thank you very much. I just wanted to point out that in terms of new challenges, one aspect that I would have liked to get your comment on is the long read sequencing, because you mentioned nanopore sort of at the same level, but it's not exactly the same thing. So you can get access to sequences that are repeated, and I think we can learn a lot about that, because there's a lot about that in our genome.
No, I think that certainly in terms of the fundamental science and getting the full sequence of an individual chromosome, definitely, the technology still has issues. In terms of using it more broadly for medicine, I think it's hard to see long reads being used in a lot of hospitals, but I might be wrong.
It may be in the future, if we think about how things developed in your case. One would not have necessarily said that.
But I mean, I think you get a lot of useful information from the short reads. I mean, there's no question that the long reads give you additional information. The question is, is it worth the cost of getting that additional information? And in terms of medicine, how does that affect the treatment that you give the patient? So I don't know the answer.
All right, thank you. I think we'll stop here. I think you can all hear me. We now have a very brief break. You can have a drink of your water, because we're not going to serve you coffee or anything like that. But talk amongst yourself. We need to mic up the panelists for the next session. They are ready to mic you up there. Take your time, but please, if you could do that. Hello? Can you please all find your seats again? I know you're very excited about those bottles of water, but it has to stop now. Yes, and nobody has drunk anything. It's just been poured for you.
Christina's disappeared.
All right, I think we will continue now. First of all, thank you so much to our keynote speakers for their very interesting and thoughtful words, and you in the audience for your excellent questions. We'll now move on to our panel discussion on a very current topic, the title of the whole thing here, namely Competitiveness through Frontier Research. My dear colleague from the European Research Council, member Luke O'Neill, will introduce the panel and lead their discussions. Luke himself is an immunologist and a professor at the University of Dublin, who has actually also co-founded several companies. Luke, please take over.
Thank you very much, Jesper. Thanks for welcoming us to Copenhagen. It's been fantastic so far. Really enjoying today, so thank you for the kind invitation. And I'm very happy to moderate this session with my esteemed colleagues. Congrats to our Copenhagen friends for putting together a wonderful panel. And we have 3 former ministers of science here, which is remarkable. They'll have an interesting perspective, I would think, on the whole question we're addressing today. And introduce the panel, we'll kick off. First of all, we have Christina Messa, who is a former science minister of universities and research from Italy. We have our glorious leader, Maria Lepton, of course, president of the ERC, is here. We have Ernst Kuipers, who is vice president of research at Nanyang Technical University and also a former minister for health, welfare and sport in the Netherlands. And then Manuel Hayter, of course, former minister for science, technology and higher education in Portugal. And then my compatriot, Dermot O'Brien, is here as well. Dermot is the CEO of Research Ireland, Ireland's premier research funder. And before he took up this job, he was the Pro-Vice-Chancellor of Innovation at the University of Cambridge. Now, before we kick off, I might set the scene for us. We have 45 minutes roughly, where we'll all speak and give our opinion on this most important topic. There'll be time then for questions and comments, so get ready for that. We're hoping to achieve a couple of things, I think. Now, we're all on the same page, so we all know what this is about. In my opinion, there are 2 things to focus on. First of all, our job as a community is to convince everybody about the importance of this topic, the importance of frontier research, obviously. Now, I mean everybody, from European citizens, who are really important, through to policymakers and then politicians. They all need to be convinced now more than ever. And because we're all on the same page, what I would like us to achieve will give you ammunition, if that's the appropriate word, to use in this debate, in these discussions. You will hopefully hear good examples, good stories to justify what we're trying to achieve here. The second thing I'd like us to achieve, I hope, is maybe some concrete suggestions. And we had one, actually, from David Klenneman already, the golden share in a company. That's a fascinating idea, a bit radical. But I'd love us to maybe come up with robust suggestions as to how important now more than ever. Now, 2 more things quickly before I ask the panel to give their opinion. I am an immunologist, as Jesper said. Now, remember the pandemic, if I dare mention it. That, in retrospect, was a very special time. Science had a primacy. People believed in science. Science was the great hope that got us out of that pandemic, remember. Borders dissolved. There was mass collaboration across the world. There was all kinds of talk of new visions for the future as to how we do science. And very importantly, the vaccines that emerged began in an ERC grant to Ugur Sahin. The RNA technology that Ugur discovered was part of an ERC grant. What did those vaccines achieve? They saved 1.4 million European lives in the first phase of the pandemic. Now, you give me an example of where a government asks us scientists to save 1.4 million people. They would bite your hand off if we say we have a technology to achieve that. And that came from frontier research. And we need examples like that to keep convincing everybody as to the importance of what we do. Of course, what's happened since then is disastrous. We thought that that was a turning point, the pandemic, in my opinion, that science would have a primacy. Things have gone backwards in certain parts of the world. I won't mention where. And I don't mean Ireland. Things have gone backwards. Progress is being threatened. So now more than ever, we've got to stand up and defend what we do. It's the most alarming thing, in my opinion. The second thing I want to talk about is FP10, as you all know, is the key program we're discussing. The negotiations have begun. And remember, Denmark has the presidency at the moment. Cyprus is next, and then Ireland will have the presidency at a very important time. And in fact, next June, we're having the council meeting in Dublin because of this, because we need to make sure that FP10 is configured in the way that we would like. It's a very important goal. The problem is, in my opinion as well, we need our politicians to be courageous. And that's very difficult for them. We need, do you not think so? I'll tell you why. It's a 5, 10, 15-year time frame. There's no votes in this for politicians. And what I mean by courageous, we give them examples, and we've had some great examples today. We're in Niels Jørgen's lecture theatre. That was a 1955 paper that Niels Jørgen published as an immunologist that gave rise to monoclonal antibodies in the 70s with Cesar Milstein and George Kohler. That gave rise to a multi-trillion-dollar industry, that 1955 paper. A second example we have is AI. They were very unusual academics in the 70s and 80s, began that process, and now it's a multi-gazillion-dollar industry. You know? But it took 5, 10, 15, 20 years, and that's why we need certainly a different view on this in terms of trying to convince people. Very important aspect to what we do. The second thing we must keep reinforcing is independence and autonomy. And in my opinion, all our opinions, the ERC has been a shining light in this regard. And that independence and autonomy must be reinforced in the ERC and must permeate the entire system, because that's where you get the most excellent science from that. And that's a very important argument that we must keep making about independence and autonomy. It must be bolstered and must be supported. And again, given the FP10 negotiations, now is the time to keep reinforcing that message. These are obvious things, but the things we must focus on. I'm sure the panelists will discuss these as well. And lastly, before I ask the panel to give their view on this, remember, it's extremely important that science and the humanities, a very important part of this, is essential to ensure our shared humanity, our security, which is extremely important part of what we're discussing, and our economic prosperity. All those tied together by supporting the very things we're trying to do. And I'll give you a one-liner to finish my introductory remarks. Europe is falling badly behind. It's only through frontier research that we will survive. It's as simple as that, and that's the message we must keep giving everybody, as I say, all the way from European citizens, most importantly, right up to our politicians. And I'm sure these topics will be ones we will come back to as we discuss this over the next 45 minutes. That's my go. Now, I'm now going to put the panel under pressure to give their opinion. I didn't send them any specific things to talk about. They're all well versed in these topics, and I'm hoping to get a bit of free association, I guess, on whatever their thoughts might be. And Maria, I may turn to you first. Can you give us your take on this most important topic of competitiveness through frontier research?
Hard, because there's so many things to say, and we've heard some today. First of all, well, Europe's economic situation is actually fairly strong at the moment. And there are many things where we are competitive and where we're doing better than those countries that our politicians like to set up as shining examples. For instance, unemployment is not high. Our working age adults are more likely to hold jobs here than they are in the US. Our life expectancy is higher. Our child mortality is lower, and living standards are generally good. But like you've said, Europe has fallen behind in certain advanced technologies, and there is a productivity gap with the US. And for several reasons, many of the cutting-edge technologies that make a difference in productivity growth and therefore in prosperity originate in the US. I mean, we've just seen the yesterday's and today's Nobel Prizes again. This would not be a problem if America was cooperative. I was interested to hear from Anne that
she stressed cooperation in Europe, and you brought it up, and not with the US. But it's got worse, of course. And they are now exploiting their advantage more than ever through tariffs, duties, protectionist policies. They're disrupting open trading order, and that affects us. And we're not in a position to stand up to that. So, you know, all these other examples are nice. We are doing well. And of course, especially the Scandinavian countries are doing extremely well there. But our power, through our lack of competitiveness and through our lack of power in industry, is actually making us weaker. I've had that very nicely explained to me by a number of Nobel laureates in economics, and we have economists here who will no doubt also be able to do that. So we have to do something, not because we want to compare ourselves with the US. I really don't care about that too much, certainly because we don't want to become like them, certainly not now, but exactly because this global context is changing quickly. It has already changed. And if we can't rely on anymore on our partners, we must find our own way. You've already said it, others have said it, and as others also have said, we're preaching to the gallery here. Productivity comes from breakthrough technologies, AI, quantum, biotech, etc. All of them began in research labs, bottom-up, curiosity-driven frontier research creates the pool of knowledge. That's another thing. It's not a pipeline. A pipeline means you put something in the front to have something, most of it, come out at the back. Some leaks, but what you put in the front comes out somewhere where it's needed. That's not how scientific discovery works. You create a huge pool, and maybe somebody can tap into that. But you have to create a much bigger pool because you don't know what you'll need. So this pipeline idea is also wrong. Anyway, funding the stuff that goes into the pool is, of course, exactly what the ERC does. The most creative Europe-based researchers to push the boundaries of knowledge. We've heard two great examples just now. And then the breakthrough technologies, in turn, are essential for researchers to push the boundaries, again, like sequencing. And the Draghi reports highlights the importance of regional innovation hubs uniting academia, industry, and investors, and maybe we can hear more about that from the Cambridge area. But it's also an approach that we can see here in Denmark, in the Medicon Valley, at the Danish-Swedish border in the Öresund region, where researchers affiliated with the Medicon Valley Alliance, especially the University of Copenhagen and Lund, include a substantial number of ERC grantees as well. So there's plenty of examples, but really we've got to work on it and do something and find the causes.
Ray, do you think the American question, we should discuss that in a sense, choose Europe is a big thing at the moment, right? What's your view of America's problems and how Europe can benefit from those, if I can phrase it in that way? We wouldn't phrase it in so many words.
I really don't think we can phrase it that way. We're all going to suffer. We so much rely on our colleagues there. They've just stopped the NOAA, what does it stand for? National Oceanographic something Association, have stopped funding for the floating climate data stations. Sure. 40% of them was funded by, 40% of those was funded. So we're all suffering. Databases, the model organism databases are no longer being funded. All my colleagues in Drosophila research, we attract these scientists over and then we say, sorry, no databases. PubMed is in danger. There is no benefit to be gained. We must just hope, as we also heard, I think Anne said it, that they recover ASAP. In the meantime, yes, let's provide them a haven. Let's do this in a non-selfish manner. If they come spend half time here, that's enough. That reinforces collaboration. So I think we are one big community. It's not us and them.
Yeah. Very nice. Thank you, Maria. Christina, will I turn to you next?
Oh, yeah.
Yep.
Well, thank you. Let me say first that the report Mario Draghi did point out very much about competitiveness. And Mario Draghi, I was in the ministry when he was the prime minister, is the one that in Italy started something similar to ERC and to fund a Italian ERC with a considerable amount of money. I mean, thinking about Italy, that is not that incredible.
I should be very humble here. You should take some credit for that.
Yeah,
should
of
be
course, I did, but I mean, without his, I mean, that is just to say that both reports, also mine and the later ones, they really know that competitiveness depends on research. So this is not the point. The point is that, as Maria said, is the pipeline. And when you talked about the story of vaccine, well, then US came first. And why? Because regulatory is different. So there is in this pipeline, there are different various factors that affect this transformation on competitiveness. And certainly our rules and regulations in Europe are one of the most challenging, let's say, factors that are affecting this. This concept should not rely fundamental research in something that is useless just because we have to put on our competitiveness. And I think that to have people understanding this, I mean, like the talk that we have been hearing today, there are a lot of products through the research story that can be can provide technological advancement and can provide competitiveness as well. But the real questions that are arising from research are others. These are sub-products. So this is something that should, I mean, like at CERN, right? They had to put the data somewhere, and so they funded the website. So this is something that people should understand. I have to say that ERC is a great success. The problem of ERC are two mainly. Well, first of all, there is an oversubscription, and the rate of success is too low. It's too low to have people just, really thinking and believing that this is the right place, the right way to do research. And in order to solve this kind of problem, either you increase the amount of finance, or you find some other way of funding, not only coming from the research part, but also from other parts. So that is certainly something that it is discouraging, although people keep on applying it. So it means that the model is right. But if you have a right model, but then you have such a low percent of success, then the measure is really weakened. The second point, I think, is that there is a polarization in the granted, I mean, let's say that there are countries that are not able to get the same grant that other countries in Europe. It's not a responsibility of ERC, actually. It's a responsibility of the single countries' research programs. Mm-hmm. And really what should be done is to have a stronger list between the European and the single countries' programs. Having statements of these countries that are trying to use the same, curiosity-driven research as well as evaluation, because the evaluation is really a big problem in many countries. And so the model is not only because many people apply. The model is because many countries should do something similar. And having this also suggested by the European Commission would probably at least move some of these countries having it. Otherwise, it still is polarized. It goes the same way, although you won 3 times, for example, but because the project is good, but you know how to do it. You know how it works. You know what the reviewers are expecting in order to win the best evaluation. So these are the 2 key points that should be, let's say, addressed. And on the other side, I totally agree with our Nobel laureate. ERC is one part of the research. Actually, collaborative research is very important. And that is another area that should be reframed in some way, because nowadays, well, there is Marie Curie, of course, which is very important, and there are the infrastructure which are moving to another chapter in the next FP10, but there is the pillar 2. There is the pillar 2 that in theory, is something very important in order to create partnership and to create this exchange of ideas and projects that are really European and do not belong to only one country. On the other side, it's very difficult. I mean, at least I don't know much about what is the impact of the pillar 2 at the moment, at present, the way it is. So I think that we have to say that the ERC should be more financed and should be a model for the countries and should have the representation of all European member states in some way on that side. On the other side, not focus only on that, but remember that collaborative research needs maybe a little, even more effort than the ERC project.
There's a concern about Pillar 2, isn't there, Christina, as I understand it?
There is a concern about
Maria was raising this earlier, isn't there, Maria? We have a fear there, have we? If fear is the right word.
We don't really know exactly what the proposal will mean. So I think we should withhold judgment for a little bit, but there is this ominous sentence of the framework program being closely connected to the Competitiveness Fund. And if you look closely at the areas, at the so-called windows, you will find the same windows in the Horizon Europe 175 million as in the 225 billion, not million, that you see in the Competitiveness Fund. And that makes you wonder how that will be distributed and whether there will be room for funding basic science, fundamental science, researcher, bottom-up science rather than top-down. So I think there is, until we hear what is actually meant, we've got to be on the lookout for possible threats.
Right. Very nice. Thank you. Ernst, might turn to you next. You might give us an Asian perspective.
Yes, thank you. Well, probably an Asian and a global.
Global as well.
European. I'm still very much count myself a European, even though I've been coming to Asia already for decades. See, for most people in the outside world, not here, but for most people in the outside world, research, and in particular publicly funded research, is something a little bit esoteric. You can do it, but you do it when you can spare the resources, the money, the people, the infrastructure, etc. Now, we all understand that it is not the case, that it has a totally different topic, and that actually it benefits us all very, very, very much so in terms of economic well-being, our health, our safety, etc., etc. And what we've seen also in Europe over the most recent decades, if you just go back till also World War II, is that actually, you wouldn't expect it, but actually during times of crisis, when there is a real need, our spending in research and innovation, for understandable reasons, goes up. And very significantly so. It was so during World War II. It was in the aftermath when we were rebuilding Europe. And most recently, we've also seen it, and we heard about it. We've also seen it during COVID. Suddenly, there was massive investments, in this case, in healthcare and in new drugs and in new ways of providing healthcare, which accelerated us with more than 10 years. So, if you look at the current challenges, and I'm looking, of course, at the economic situation and challenges that we have in Europe, but you can also look at our aging population. The fact that over many years, if you look at healthy life years, my background is medical, so forgive me the examples, but our healthy life expectancy has actually declined with all the developments. But also if you look at food security or energy transition or, for instance, climate change, we talk about the plus 1.5 degrees Celsius globally. We should talk about the already established plus 2.4 degrees here in Europe, in a continent where soon 80% of the people will live in an urban situation. So climate change is the #1 threat to our health, as the World Health Organization also has addressed. And we have no real understanding how to tackle this. So all of these challenges really ask for a lot of investment, and it should be public, government or EU-led funding, first and foremost. And we've seen, and for instance, Mariana Mazzucato has published a lot on it, that is actually very well established and well paid off. It pays off. And then we can discuss whether it should be 180 billion in 7 years or 200 or 220. Let me just briefly give you the comparison with Singapore, which is, because also you asked it, and which, as you know, is again and again, if you look at international competitive scores, usually Singapore is in the top 3 worldwide. So Singapore has, ever since 1990, Singaporean government, since 1990, every time again with 5-year plans, 5-year investments, called research, innovation and enterprise, but it's government funding. For the next 5 years, the period 26 till the end of 2030, the investment from government will be 37 billion Singapore dollars. Now, just to do the translation for you, that's approximately 25 billion euro for a population of 6 million people. It's a very small island. So just do the translation. It means a government investment of 800 million euro per million inhabitants per year. Now, all of the ambassadors and everybody here can do the math, what it means for your individual country, whether it's Ireland or Denmark, 800 million euro per 1 million inhabitants per year. If we do that for the EU, we would come to totally different numbers. Now, it's not like try to reach that target, but what it simply shows in the example is it pays off. It literally pays off. And it's invested in this case mainly into 2 main universities and 1 government-affiliated applied research center. And that explains that, for instance, the university that I'm affiliated with, Nanyang Technological University, is only 35 years old. It's a baby compared to European universities, but it's already in the absolute global top. Now, the point to translate that is, I'm absolutely convinced that we have beautiful examples here from Lund and from Cambridge. We can totally do the same in Europe with our hundreds, literally thousands of universities. We can do. But we have to convince people that we have to invest, and that's what will actually will benefit us and help us to address the challenges that we face.
It sounds like we have to frighten them into it then. Is that what you're thinking? In other words, in the past there's been emergencies and they've been frightened.
Yeah.
Now we should fear this, should we? I mean, it's a real fear, isn't it? And we hear about China all the time and the competitiveness and all this issue.
So I made
that example you just gave is robust, frightening example for Europe to listen to and wake up about, I would imagine.
Yeah, I stay with Singapore, but if you ask China,
Yeah.
if we, for instance, go to Tsinghua University as one of the, for those many of you will know, a top Chinese university, the available funding is fourfold the one that we have at the Singapore University.
Yeah.
Fourfold.
Do you think that's the most powerful argument we can make, Ernst?
Yeah, and mind you, it's not like this. This is not. It sounds like something that's. I'm totally not convinced. This is not lost. We have a very large power. We have excellent scientists.
Yep.
We have all. But let's invest.
Yeah. What gets me as well is, I meant to say this, that there's been massive discovery in Europe for the past 20, 30 years, fundamental discovery,
Yeah.
that we could now leverage extremely effectively. There's a whole treasure trove of information. We heard Jesper say earlier, the patent situation is remarkable from the ERC grants, for instance.
Yeah.
You know? That could be tapped into. I think we keep banging that drum as well, to say there's things to draw on here already.
Yeah.
And I always feel that to convince people of anything, you can't say we're desperate.
No.
You've got to say we're already somewhat successful, and we need this next step now to realise that success is the way to do it, I think.
Yeah.
Very good. Dermot, I might turn to you next as a representative of a whole country in so many ways, as CEO of Ireland. And having been in Cambridge, what would be your take on this topic?
Well, my first take is I should have gone to Singapore. It's
Instead of Ireland. Oh, I hear that. Did they offer you a job there as well? Because he was in demand.
Yeah, well, I thought I'd just provide some perspective from an Irish point of view, and then maybe to pick up on what David was talking about earlier, some perspectives from Cambridge. I mean, the first perspective I had was very much ties with what Christina said, which is that we need to have very strong alignment between national and EU funding. I think if we don't run the kind of core basic research driven programs nationally, it's very difficult for people to build the capability and competence to compete at a European level. So it's really important we copy the model of ERC. I mean, we're fortunate enough to have that within Ireland, but I'm not sure we have it at the right scale for what we need. And the other piece that I think is becoming challenging is investing in the research infrastructure that you need to really sustain competitiveness at a national level to compete at a European level. And I think that is becoming important to really begin to think about how we align our national investment strategies with our European investment strategies. So as an integrated outcome, we have a stronger and more competitive environment. So I think there's a lot that can be reflected on there. I think one of the other challenges we have linked to, say, what we're experiencing in Ireland, but also linked to the question earlier about Durham and what we can learn from Cambridge is, I think great science can be distributed, but I'm not sure great innovation can be distributed to the same extent. You need a critical mass and anchoring of not just great science, but the entrepreneurs and the venture capital and the corporates that can really align to build that scale. And to some extent, in the story that David was communicating from Cambridge, there's a real benefit from having that capacity. And so I think we really need to really think about, do we have enough scale in some of our universities, and how do we build those partnerships and collaborations across our universities to really have the scale to build that excellence and compete? In Cambridge, we would have been spending a research budget that would be equivalent to the national research spend across the island of Ireland in one place, with a kind of concentration and density that allows you to leverage that return in a different way. And that's not to say that the outcome should be we build super concentrated universities in single locations. But I think we need to really ask the question about how we connect our excellence in science in ways across our ecosystems to think about how we can leverage the advantage of that. And to some extent, there's been some work in the UK around that, around dedicated venture funds looking at alignment with the university system. And most of the big universities of the UK now have dedicated venture capital funds that invest in the technologies coming out. In places where you don't have the scale, like in the north of England, they've created Northern Gridstone that works across Manchester and Sheffield and Leeds and Liverpool, where you can begin to get the competence and capacity and expertise that you need to think about these challenges, but distributed across multiple institutions to leverage the scale that comes through partnership. And I think that sense of how we build a community of our ERC researchers and build maybe citywide or region-wide ERC propositions or propositions that think about scale of research excellence, but also connected to the bigger opportunity around innovation, is I think something we probably need to think about as we think about the next phase. Because if we double funding, which is absolutely what's needed, how we build the most efficient mechanism to leverage the outputs of that within Europe is going to be, I think, a challenge. Which brings to the third piece around capital. Now, capital to me has kind of a couple of components. You've got proof of concept funding and translational funding that are needed to take the technologies and research that outputs that come out of the frontier research. And then you've got the kind of private capital, the venture capital that David talked about coming in to support it. My sense is that the proof of concept and translational funding piece of Europe is still not competitive to what you see in other jurisdictions, particularly, I guess, in the US, but also what we're seeing now, particularly in China. So I think we really need to also reflect on, as we strengthen our ERC investment, how do we strengthen our translational capability, which I guess will come through as some of the other vehicles being looked at. But aligning that, I think, is going to be very important. On the venture capital side, I mean, I think there's another interesting example from the UK in recent years where they have developed the Mansion House Compact, which is about unlocking institutional pension fund investment to go back to be invested in UK science commercialisation. And so really just unlocking 5% of institutional capital and refocusing it on that translational agenda unlocks a huge amount of different capability to build not just great science, which of course is the foundation of everything, but then to build the economic outcomes of that and keep it localized within an area. And I think, you know, the golden share is a model that's been talked about, but I think a more effective model, to my mind, is having sovereign capital investing in companies within a geographical region, which doesn't force those businesses to take international capital to scale in the wrong direction, geographical wrong direction, which is often what is forced into businesses at that medium to large-term scaling piece. So I think looking at both that translational investment piece and that institutional capital piece, I think would be a really powerful combination. We've certainly seen from best practice in the US now that people have moved away from this idea of venture capital investment to venture building, you know. So you don't just give money in, you're bringing real expertise and depth and scientific knowledge and capability. And so one of the things we should be thinking about also in Europe, and maybe actually very much linked to the ERC agenda, which has got a huge amount of that kind of incredibly rich IP that's coming out of it, is how do we train and develop that next generation of deep tech and scientific investors to partner with our deep tech and scientific research community to build that kind of integrated output that I think will be powerful. So I think there are some challenges there about aligning our national agendas directly, but also really thinking through how we create that critical mass and scale and how we connect it to that translational journey.
I think it's great. We've come a long way when an Irish guy is praising the UK. That's remarkable progress. But just to touch on that slightly more, we discussed this earlier, but that pension idea is a remarkably innovative idea, is it? Because clearly the UK identified lack of capital as a key issue here with the VC community and various things. And they must have said, let's try and do something. And there's about 5% of pension funds might go into startups. I mean, that's a fantastic idea.
Well, not just startups and scale-up capital. But I mean, clearly that's the model that you see in the US and in Canada. You know, and often it's, you know, the Canadians Teachers Fund is paying for all the venture capital is going into the UK, you know. And I think the challenge here is that if you think about these economic feedback loops, you can raise venture funds in Europe, but a lot of that capital is still coming from outside of Europe, which means that the economic benefit and return of that is not staying in Europe. It's going back into the US or Asian markets, or now more recently into the Middle Eastern markets. And so in some ways that's fine, but what you're losing is that, you know, we were talking about that pipeline, you know, but this is a very leaky capital pipeline, because actually what we're finding is that European science and companies are generating wealth for those outside of Europe, and we're not seeing the feedback loop coming back to now is to recycle and invest in what's coming out of Europe next. And I think the only way we can close that loop is to have European capital being predominant in driving that. But if we do that, we also need to build the investment capability to go with the capital. Because if we don't have people who understand how to build deep tech companies, it's going to be a real challenge.
Very good. Thank you, Dermot. Manuel.
Thank you.
I'm leaving you to last on purpose because I'm sure you've got much to add to this, especially based on our discussion at breakfast. So give us your take on this issue.
Thank you so much, and I will start with a statement. We should be proud. We should be very proud of the European projects. And we know today more than ever that we live in the most robust region at the world level, and also the most efficient per resources involved or invested. The point is that by being proud of the European project, we need to understand that we are facing a new complex of uncertainty, and therefore we need more than ever scientific activism. I'm speaking for scientific leaders like all of you. We need more scientific activism to face this unique opportunity in Europe. And don't mislead. Actually, Nature last June published a report with several surveys throughout Europe where clearly showed that population at large in Europe believe in science, but scientists are less and less relevant for policy making. So we need more and more, in my view, of scientific activism, because this new complex of uncertainty that we are living is new. We know that science have been a battleground forever, but is more than ever. We have an accelerated rate of technical change, as clearly presented today, particularly in association with the rise of Chinese science. We have a clear increase in the fragmentation of multilateralism. More and more, we have also something new, which is the increasing polarization, political and social polarization of our societies, with populist movements, also in Europe, being supported by young generations. And this should really be a matter of key concern for us. Last but not least, we have an increasing vulnerability associated with new or emerging societal challenge, including mental health, including the economic inequality to access innovative pharma, and certainly the climate change. So, by being proud of Europe, whose lessons learned of the best we have done. And certainly that is the European Research Council. We have Maria here, but we have two former ERC presidents in the audience, Helga and Jean-Pierre. And we need to understand why ERC is the jewel of the crown in the European context, and then derive implications from that. If we look essentially at the last 4 years, as we present in our report, we know for many different that, for instance, almost 2/3 of the new startups created in Europe, and we Europeans over the last 5 years have created more startups than the United States. So that battle has been already solved. But we need to understand that about 2/3 of the startups being funded through the European Innovation Council, derived from the frontier research funded through the European Research Council in periods of time which vary between 2 and 4 years. And this type of results, which we were used to go to the United States to show, now we have them, as presented before, in Europe. But at the same time, we need to figure out that the European budget is very small. The European budget, for instance, just for research and development, only accounts for about 6 to 8% of the overall European research budget. And when we look at European budget, data from Horizon 2020 and from the first 3 years of Horizon, Europe clearly show that, with notable exception of DRC, the Marie Skłodowska-Curie actions in DIC, which represents only 22% of the overall budget, the remaining 78% has been distributed through consortiums, which in average now have 11 partners, where each partner receives in average 127k euros during a period of 3 years. So what we know, and our plea is that the framework program, particularly since FP7 and essentially Horizon 2020 and now Horizon Europe, has become an excellent tool to distribute money. But it is not necessarily the best tool to do science or to address industrial competitiveness or to address emerging societal challenge, with a notable case of this 22%. Why? Because DRC has been funded, as you did it, with an independent, complete independent councils. Member states clearly define the budget, but once the budget is defined, is an autonomous governance. And that is the only program in Europe that does it, because this is so noble that we need you all to really speak with European citizens, with members of the European Parliament, with governments in all our member states, to show that our lessons learned is to make the jewel of the crown a clear example how to govern the rest of the framework program. Let me conclude that this should be a serious debate, that only people like you can take it at large. I was a research director and have been involved in framework programs since the very first framework program, and decided to go to the political world to try to change things. So don't blame politicians. They do whatever the pressures that they receive from different political environments. So we need to be active in making the best of the best in Europe as a trend overall. In a very recent debate promoted last June and July by the Joint Research Center, based on our own report, the Draghi and the Letta reports, actually there was a number of issues very interesting, notably by Luke Soot, Karin Kattel from University College London, but also Sylvia Serger from Sweden, where they argued that in order to make this opportunity unique in Europe, we need to make sure that the investment in research and development, and say science investment, is out of budget control. Because we know that most of Europe is under pressure due to budget control. The only way, they argue, to do this is to consider a better articulation, potentially in the coming decade a merger between DRC and all the national science foundations, and to make science out of budget control, and in a completely different way to decentralize for the European regions the innovation funding. We know this will be very difficult, but we need again to use lessons learned from this excellent tool we Europeans have been able to implement over the last 17 years, which is the European Research Council. And I'm sure most of you know, 20 or 25 years ago, when Philippe Bousquin launched the idea, no one in Europe believed that the DRC would have been possible. So we have done it. So now we need to really speak loudly to all our citizens and say, this is the way to go, is the jewel of the crown in Europe. And the remaining of the FP10 should follow this practice. That is the reason why we suggested the Commission that the model, the governance model of the European Research Council should be used in all the other remaining programs. But don't forget, the proposal presented by President von der Leyen in July is an actional very good first step, but the budget is not enough. The 175 billion is much lower than Draghi and our proposal between 220 to 220. And if we look back to what happened 7 years ago or 14 or 21 years ago, we know that the initial proposals have always decreased. So we need to face it properly. There is a budget problem in Europe, so we need definitely to enter, and Mario Draghi last week in Brussels open again this discussion. We need to go to debt, and we need to build new European own resources because we need more public investment in Europe. So by being proud of the European project, and we should be, or actually Paul Krugman, Nobel laureate in the economic services, last week was arguing Europe is doing much better than Europeans usually say, and we are doing well, but we must do much better, and in my view, we need much more scientific activism because it depends on your experience to show to every European citizen, to our representatives in the European Parliament, in the national parliaments, that DRC is the model to follow in terms of governance and in terms of the way we distribute funding, by complementing it with cohesion funds and European public procurement. Again, the vaccines was a clear example. Is originated in fundamental science. For the very first time, it was used an European public procurement system to buy vaccines, and it was the distributed vaccines to the population. So I will argue that we know how to do it, but let's do more of the good things we have been able to build in Europe, and DRC is one of them, certainly together with Marie Skłodowska-Curie Actions, and we have also with us the president of the MSCA alumni. Today was very clear how these European instruments have become so important for the beauty of Europe. So let's do more and better of the best of our programs.
Round of applause for Manuel. That's a great way to finish the debate. Thank you, Manuel, very much indeed. That's a call to arms, you know. Scientific activism is a key part of this, I guess, is your message. Now, we might throw this open to discussion. Does anybody have any questions or comments to add to this discussion? Oh, there's a few over there, actually.
It's good.
Do we have a microphone?
Do
you want to shout?
No, yes.
It's coming. Over there. Over there.
Good. Raise your hand again.
Yeah, that's for that. Yep.
Okay. Thank you. I'm Henrik Wiggener. Hello.
Yep.
Former rector of this university, also former chief scientific advisor to the commission, and many other things. My question, now that we have 3 former ministers of science, is how come that the member states spending, the public spending on research remains so relatively low in most EU member states? Because when you talk about the jewel in the crown, when we talk about the budget, the EU budget for research, it is not enough to lift Europe. We need member states to invest more. We need member states to have junior ERCs. Basic research councils in member states have to be the training ground where scientists can develop and become future grantees of the ERC. But we're still looking at most member states spending less than 1% of GDP, that is public spending, for research. How come this doesn't change? It seems to be chronic. And could there be a solution in the new increased spending in, let's just use the term, security?
If you allow me, there is a very easy answer, and I pass also to my colleagues. Is the only criterion which has been used over the last 30 years in Europe is public debt.
Public?
Public debt. finance ministers and prime ministers are judged by the level of the public debt. If you look, we all invented, as European citizens, under the European authority, a tool which is called the European semester, where all governments every 6 months need to report to the Commission what they are doing. The only variable that is considered is public debt. I spent 14 years in government fighting. Actually, we went from 0.5 of GDP to 1.7. We know that we cannot do more because of public debt. That is the reason why Luke Soot and Rainer Kattel and Sylvia Serger recently mentioned the only way to increase the necessary investment in research is to make science out of budget control. If you don't do it, you will never be able to do it. And we can do, I can give you the examples. There are 4 countries in Europe that did it. Sweden, Belgium, Germany and Austria, because of 2 things. They have increased the number of researchers together with the funding per researcher. All of them have more than 11 researchers per 1,000 employee, but also funding levels per research above 200,000 euros. If you compare, for instance, Austria and Germany with Portugal and Slovenia, we all have 11 researchers per 1,000 people. So we have also grown, but our funding level is 1/3. Why? Because the finance minister and all the prime ministers in the right and left never allow us to touch in the salaries. Why? Because of the constraint of public debt. So you will never get it if you don't avoid that limitation. Actually, it's interesting that 2 weeks ago in Brussels, in front of President von der Leyen, Mario Draghi, the former president.
Well, you're going to have to speed up.
Yes.
I will.
I apologize.
But Mario Draghi mentioned again, either you go to debt and create new European own resources, or we don't have the necessary levels of public investment in Europe.
So there could be a solution, potentially, it sounds like. Christina, do you want to?
Well, certainly public debt is a problem for Italy as well. And I add another thing that is cultural belief in science, unfortunately. So the level of trust in science is not taken up by politicians because the citizens are not that much fan of science. And so, of course, you win the election if you talked about many other things and not science. And that is something that I think is happening in many more countries, not only in Italy. And there are 2 things that I want to point out, because, I mean, okay, we have to be proud, but we have also to know our limits in Italy and in Europe. And one of the limits is that our universities are too traditional. And we are really are unable to answer the needs of today. I talk about, I'm saying this we because I'm an academic. I mean, I've been rector in Milano and I know very well universities. And we are too traditional. We are not able, except for some countries like the Netherlands, for example, but generally speaking, we are not able to introduce interdisciplinarity. We are not able to really change the way we evaluate our researcher. They are still evaluated in the same old way. So I think... And teaching English, for example. I mean, if you talk to humanistic, of course, they want to they know how language is important. So, but there is something that a trade-off that has to be found. So, if we want to have more, be financed more by the public, having said that private financing will be certainly stronger than the public one in few years' time. That thinks about all the technological research. I mean, it's all private nowadays. It's not public any longer. But having said that, we have to deserve this by changing something in our rules again, and in our attitude as well.
Ernst? Yep.
Yeah, I would like to add another remark, and I don't think that the primary reason is budget constraints, but the first one is short-sightedness. It's simple short-sightedness. If I look at the Dutch situation, for instance, we had an investment fund for research of 25 billion euro over 5 years. With a new government, and a new parliament, this was stopped after having spent 11 billion, and the remainder of the money, 14 billion, was largely put into literally reducing tax on gasoline, which is almost like literally burning the money. It's short-sightedness. So it comes back to the same story which we already had, which is what we have to do is really create the feeling of urgency and say that we can together, with European programs, we can address these urgent needs. They will not be solved for us by others, but then we need the funding. When it comes to of course there is financial constraints at the end. All of us who've been in government know that the Minister of Finance is your colleagues who is the last one to move, for good reasons. So if we have the budget constraint, then other ways is of actually finding and getting the approval from the Minister of Finance of shifting budgets around. If I just look at my own former budget as Minister of Health, it was the largest one in the Netherlands from any part. It's like 110 billion per year. Of course it has to be spent on healthcare, but can that also include parts of innovation in healthcare? Of course it can. But you have to have a site which is further than just the next year or the next 3 years.
Very good. Thank you, Ernst. Any more questions? Yep.
Thank you very much, and good afternoon, everybody. Kurt de Ketelaar, League of European Research Universities. I would like to come back to the budget discussion that we had with the panel, and I would like to call upon all of you here this afternoon, in view of the presentation that Maria is going to give next week in the European Parliament in the Budget Committee, that all of us should think about what is the best strategy now. Because we now have this seducing proposal on the table of 175 billion euro for research and innovation in the period 2028-2034. And although there is no official figure yet for what the budget of the ERC will be, we all know that the unofficial figure which is floating around is 31.5 billion euro. And obviously, Commissioner is very pleased with this because she can say now to all of us, the budget of the framework program is not only going to double, but also the budget of the ERC is going to double. Over the summer, I was quite supportive for this approach because I was still convinced at this point in time, or at that point in time, that also the ECF, European Competitiveness Fund, would have a certain amount of money available for basic frontier research. You know, as was said this afternoon, that we there see a budget popping up of 220 billion for the 4 policy windows. So 175 combined with a part of the ECF for RNI could make a nice figure which could convince us at the end of the day. But what have we learned 2 weeks ago? We have learned 2 weeks ago that the position of DG RTD is now that no funding of RNI will happen through the ECF. And DG RNI has been very clear on that. The ECF will not fund RNI, so that means that we can forget about the 220 billion euros which are there for the 4 policy windows, leaving for us, at the end of the day, only the 175. And if we then look at what is the explicit commitment in the budget proposal which is on the table now for fundamental research, then the only thing of which we are sure is the budget for the ERC, if that would be confirmed as being 31.5 billion euro. Because I don't trust any potential figures for basic research in Pillar 2, if Pillar 2 is fully dominated by the ECF. I don't trust any kind of figure in Pillar 3 for basic research, if the EIC is heading in the direction of dual-use funding and even defense funding. So that means that at the end of the day, we have heading 2 of the MFF proposal, which is 400 billion euro for competitiveness. And of that 400 billion euro for competitiveness, the Commission is now saying to all of us here, of those 400, we only foresee explicitly 31.5 for basic research. I don't know if you read the opinion piece that I wrote on that last week. Not everybody in Brussels was very pleased with that opinion piece. When I said, hey guys, you want to compete with the US, you want to compete with China, you have those huge ambitions. And the only thing that you can do is give, for sure, 31.5 billion euro of a budget of 400 billion euro to basic research. Well, in fact, this is very disappointing, if I use an understatement. Very disappointing. So the strategic question is, for all of us here today, with what kind of message should Maria go to the Parliament next week? In a sense, are we going to say 175 and 31.5 for the ERC is fine for us? Or are we going to say, first of all, well, the 175, we first of all want to have a redistribution of that money over the different pillars, and certainly Pillar 1 should get more, in particular, ERC and MSCA. Second strategic question for all of us here is, are we going to reopen the proposed distribution of money over the framework program and the European Competitiveness Fund? Because both of them are in the heading, number 2, of the MFF proposal, composing this 400 billion euro budget. My proposal is, as Secretary General of the League of European Research Universities, we question the division between the ECF and the FP, and within the FP, we ask for a bigger share for Pillar 1. I leave it up to you. I hope that we can discuss about this later today, over dinner, whatever. But these are strategic questions for next week, Tuesday.
There's no pressure, Maria.
The only second remark that I want to make, the only second remark, which is much more down to earth, and okay, I'm a lawyer. At the end of the day, I have to make this remark here. The suggestion which was made for golden shares, I'm very sorry, but the European Court of Justice doesn't allow golden
yet again,
shares
hidebound.
because it violates the free circulation of capital within the EU, and only if you have a very specific overriding public interest in very narrow terms, golden shares could be accepted. But that's very exceptional. Thank you very much.
Thank you very much. Time is against us. Has anybody got any pressing question that they're desperate to ask?
Pressing question.
That they're waiting to ask? Is there, there is one?
In the back, all the way
the
in
last
back,
question.
In the
At the
back.
back. God, they're fighting for it now. They're great. Didn't that time fly by? I thought it did anyway. I don't know what happened at the time.
Hi, I'm Mustafa Munishorov, Executive Director, Marie Curie Alumni Association. Half of the question was already raised by Kurt, so thank you very much. But I would like to reflect on another point and a question to the 3 former ministers. There are, for €1 investment, we get €1 investment in R&I, we get €11 return. That's the statistics from the Eurostat. We all know scientists are being active in policy, discussing with the policymaker. We are not doing what agriculture sector people does in front of the parliament, but we are still active. In this room, we all know the value of the research and innovation. But Manuel Heitor, your report suggested 220 billion euro. We got the proposal 175 billion euro. Not only that, we are trying to reinvent the wheel, which is working. One of that is the ERC's governance, has been basically, there are rumors about the governance structure. So how can we and you, from your view from the member state and the work from the member state, convince the Commission not to reinvent the wheel, especially for ERC, MSCA, which is already working? Thank you very much.
Yeah. That's a rhetorical question, isn't it, Manuel, unless you want to address it? Well, I think we've answered it already.
My easy questions to the two comments is, first and foremost, follow Mario Draghi last week in Brussels, say 175 is not enough, we need more. Don't forget that we have time. This discussion will not happen overnight. I believe that Maria doesn't need no recommendation. She knows much more than all of us together how to do it. But this is a long time discussion.
We need the member states.
Exactly, of 1 year. And don't forget that the European Parliament is not, do not operate in vacuum. Actually, it operates under a strong, or it should be a strong coalition between at least three, mainly two big parties, which are now in big fights among them. And we see Ursula von der Leyen yesterday in the European Parliament. So this is also a political question. It requires time, and we need to fight, in my view, for more funding and a better governance, making use of the ERC experience over the last 15 years.
Ernst, very quickly.
I think with that, your points are totally right, and I think with that we should reiterate and again and again and again tell the same story, while on one hand posing and asking and setting the large challenges that we have, but then also pointing out that we had two beautiful stories from very senior researchers who tell us about beautiful stories about their career and how you start and what it pays off. You do how many 500 ERC start grants a year? About
1,000 over the whole. I mean, Anna didn't have starting.
So if you would have the opportunity to do 5,000 or 10,000, would we have the faculty and the young people? Yes, we would. And if you would do the evaluation 5 years on or 10 years on, you would know that, okay, 10% might have failed. Too bad. A few publications, nothing else. 10% would have done so-so. And the whole, but at the end, even purely in economical terms, it pays off tremendously. So again, looking at the Singapore example, give you one. So one university doing this with 60 young people a year, same amount of money, about €1 million for 60 people across the full range. And if you do the analysis, and we've done it again and again, you look 5 years on and 10 years on, purely in economical terms, the return on investment is huge. If you look at it in terms of societal return, the return on investment is even far larger. And that's the story that we have to tell.
Great, thank you, Ernst. Now remember, we're here for the whole week, by the way, so please engage. We're a community all together. We look forward to more discussions on this very important topic. I want to thank the panel, give them a round of applause. And now hand back to you.
Yeah, thank you so much to the panel for this. I think it was a fantastic discussion, really, really helpful. We started out with the French Revolution, and now you've just been told to go to the barricades, throw some stones.
The resistance begins here.
And we will continue the discussions on the 15th floor. There will be helpers out there to get you up to the 15th floor. We will have a direct view to Copenhagen's rainy season. It's dusk now, but it'll be all right. Okay. It's very important that you do not need to take your coats. The whole wardrobe will be brought up to the 15th floor. Okay. Just remember to take it from up there when you leave. Of course, if you're leaving now, some of you might have to. You'll have to go out and get it, but don't worry about if you're going to 15th floor. There will be quite a few elevators, but it's a critical thing at the University of Copenhagen. We really don't want people to go fast up and down. So please get out there as soon as you can so we can get up and get some drinks and some finger foods and some more discussions. I think that's about it, except that those of you going to dinner, there will be a bus right outside on the street out here. It leaves 7:15. Don't be late, or you'll be left behind. Sorry.
Good.
Thank you.
Thank you.
Okay. Thank you. Very good. Very good. Super. Thank you.
You have quite a